Hey, what's going on everyone? I hope this video finds you well. My name is Jonathan Bradell, and today we will have another installment into the Modern Numerical Techniques series. However, before we get started, I realized while planning this video that this format that I started with was pretty restrictive. So I'm going to modify it a bit for future videos. I'd like to eventually show code or dive deeper into more complicated algorithms. So I will dedicate part 2 to tensor network type approaches. This video won't be on its own. I will be adding parts 2.1, 2.2, etc. On different things like matrix product states, matrix product operators, and different algorithms we can perform on these new objects. The exact diagonalization series will similarly get parts 1.1 and 1.2, where I'll show you how to block diagonalize, and I'll probably showcase some of the code that I'm using in some of my active projects. So part 3 will similarly be dedicated to Monte Carlo type algorithms. So with this in mind, let's jump into it. In this video, we'll begin our journey studying tensor network type techniques for many body problems. We will introduce what tensors are, and we will also talk about a nice graphical representation for them to talk about numerical techniques. And then we will show one example algorithm to start us off called Tensor Renormalization Group, which will allow us to study, for example, the two-dimensional Ising model at finite temperature. Okay, so let's first discuss what a tensor is. A tensor, in our context, is a generalization of a vector or a matrix to higher dimensions. A rank 1 tensor is a vector, and a matrix is a rank 2 tensor. Notice how the rank here is telling us how many indices we need to describe the object. We already know how to combine rank 1 and rank 2 tensors in the form of multiplication. The ith entry of our new vector x here is taken as the sum of the entries seen on the right. We sum over the multiplication of the ith row and the jth column of the matrix times the jth entry of the vector. And for the purposes of our discussion here, we refer to this as a contraction over the j index. But now we are interested in more general objects that can have many more indices, and similarly how we might have them interact with each other and multiply into each other. For example, we might write some general rank 3 tensor as a product of 3 other rank 3 tensors. It's easy here to potentially get lost with the indices pretty quickly, so what we're going to do is we're going to introduce a nice pictorial representation of a tensor. The tensor object itself is represented with a ball that we can give some name, perhaps A, and its rank is signified by the number of legs sticking out of it, pictorially representing the indices required to describe an entry of the tensor. So in our picture here, we have a matrix that we've called A. From this picture, things like matrix to vector multiplication, these things become immediately intuitive and self-explanatory. Connecting these two objects by a leg means that we are contracting that index specifically and forming a new object that we see below as the new vector x, which only has one index. Okay, so now that we have the basis for describing tensors, we are almost ready to introduce tensor renormalization group. But first, I think it's nice to have a model in mind to introduce the algorithm, despite it being, quite a general algorithm and applicable to many sort of classical Hamiltonians sitting on lattice. So for this video, we will study the classical two-dimensional Ising model on a square lattice, which is a minimal model that undergoes a thermal phase transition that's really interesting to study. So for the example that we're interested in the Ising model, we will write the energy equation in the following way, where the sigmas can take values 1 or -1, representing a spin up or a spin down. The spins interact with their nearest neighbor, and they also feel the presence of a magnetic field. Here we are interested in the finite temperature properties of this model, so we are concerned with computing the partition function z as a function of temperature as seen here. The curly braces for the summation for the partition function tells us that we should sum over all possible microstates so that each spin must take its value -1 or 1. If you're unfamiliar with this, I recommend my playlist Getting Started on this channel that covers the derivation of the partition function, where it comes from, and why this allows us to compute everything we might be interested in for our model at finite temperature. So the picture we have right now is that we have some system of Ising spins on a square lattice as seen here, where we have sort of sparsely, you should picture that the spins are everywhere on the lattice, but I've sort of sparsely put them there. Neighboring spins interact with each other. That means that if you have two lattice sites that are connected by a bond, those spins will interact with each other. And we picture the balls in this picture as the lattice sites here, and assume that we're only interested in the spin degrees of freedom on this lattice. Our first step in constructing our algorithm is to notice that we can rewrite the partition function in terms of a network of tensors. First, let's zoom in on 4 spins, and let's rotate the picture sort of 45 degrees, and we will label our example spins as sigma u, sigma l, sigma r, and sigma d for up, left, right, and down. From here, we will then identify a rank 4 tensor that identifies the contribution made by the spins interacting to the partition function, and here the superscript 0 is put there for convenience later, as we will be creating A1 and A2 and so on as part of our algorithm of coarse graining these tensors, as we will see as we sort of move on in this video. Okay, so identifying the tensor A with 4 indices is actually pretty easy. Writing down the contribution, we get the following expression, and this is the contribution to the partition function. The equation itself is a little long. We inserted 1/2 on the field term, as each of these terms will appear in one other tensor as well. So we can now rewrite our partition function as a gigantic tensor network contraction, which is a gigantic sum given here, which eventually gives us a scalar. As you have probably already guessed, if we have n total spins, we have half as many tensors, and the special t trace here is called a tensor trace. It tells us to sum over all of the indices in this extremely complicated way that we see on the left-hand side here. Alright, so what we have done here is taken our lattice of big N total spins and replaced it with a lattice of n over 2 spins, or half the amount of tensors compared to spins. We are still stuck with an extremely complex sum to evaluate, but the goal here is to reduce the problem to something more simple. So in this case, the tensors, and this gives us a language to employ a lot of extremely powerful techniques to the tensors to reduce the problem. The first thing we are going to do is we are going to factor our tensor A in two different ways. Pictorially, we represent the factorization in the following way. First, we group the indices up and left, and group the indices R and D. And we factor our tensor into two new tensors that we call FR and FL, where these new tensors are represented by a triangle pictorially, and we have introduced a new inner index to connect them. We similarly introduce the other factorization where we instead group up with right, or U and R, and we group L and D, introduced as FU and FD. Since all of our tensors are identical, just with different indices, we only have to do this once for each factorization. Notice the colors here as they will come to represent which F tensor I am referring to. So red, for example, will always mean FR. Okay, so now I know that this is probably a little abstract and you don't yet know how this factorization works. But first I want you to appreciate what this might do for us, creating some type of flow for us to evaluate the sum efficiently, the sum being the partition function. So right now what we have is we have a big lattice of my tensors A0 here, and what we're really imagining is an extremely big scale of this. So this is just some cut of my system. We have a macroscopically large amount of these tensors. So here I've labeled everything little a and little b, and on each of these tensors, we really have a naught, but we've alternated little a and little b in such a way where we are going to factor a naught according to one factorization or the other, as seen just before in this video. So perhaps on A we'll factor into the FR and FL, and B we will factor into the FU and the FD factorization. And this will allow us to identify a flow for our algorithm. Doing the factorization this way for the little a's and the little b's allows us to rewrite our tensor grid as the following factorized tensors. Again, the colors here mean the same tensors from the factorization as before, and we will imagine this pattern goes on in sort of all directions as our original tensor network picture did as well. So there is a macroscopically sort of large picture here, and we're just sort of zoomed in onto a tiny part of it. So we identify the boxes inside this new representation as our new tensor A1 in the following way, where we have contracted or summed over all of the indices internal to the square of triangles and left the ones coming out as our new tensor indices for our tensor A1. Okay, so this describes a nice flow of tensors. We can similarly apply this factorization again to A1 and find A2 and continuously repeat this process. Note that in the picture of the A1 tensors, we now have n over 4 tensors left, so we have again halved the number of things we need to track. But let's introduce the factorization method more mathematically, and this will allow us to also introduce an approximation scheme into this calculation that will allow us to approach extremely large system sizes. So let's talk about our factorization in more mathematical detail. And really all it is just a singular value decomposition. For the sake of time and the fact that the procedure is identical, I will show you only the following factorization, which is the one where we group the U and the R indices and the L and the D indices. The first step is to deform our rank 4 tensor into a matrix by grouping U and R indices into one index, and the same for the D and the L indices. This gives us a matrix that we call A0. We can then factor this matrix using the singular value decomposition. We can write our matrix A0 in terms of this factorization. So this is, we have some new matrix U, which is a unitary matrix. S is a diagonal matrix with non-negative real numbers on the diagonal. We've just separated it into 2 square roots because of this fact and the way that we're going to group everything. And V is another unitary matrix. So although we know that the dimension of each individual index is 2 for our first step, we will make sort of the following example of a step in the algorithm generic in order to convey what the algorithm will look like for all of the following renormalization steps as well. So let's let one of our indices, let's say U, run from 1 to chi. Chi here is our so-called bond dimension, and it will be the thing that we need to pay attention to for storage properties and time order complexity of the algorithm. So we can now straightforwardly write out our tensor A in terms of the singular value decomposition in the following way. And this lets us straightforwardly define our expression in terms of our new tensors f up and f down. And the important thing to note here is that everything we've done up until now has been exact. And to introduce our approximation scheme, most modern libraries for linear algebra will usually give you back the singular values ordered from largest to smallest. So our approximation scheme takes chi prime total singular values from the matrix S and throws away everything after that, and hopefully those terms, given that chi prime is big enough, hopefully those terms are relatively small and we keep all of the important information. So this truncation chi prime is a controllable parameter, and again it's justified by the intuition that tells us that we are probably throwing away sort of local information that shouldn't matter too much once we start zooming out and we look at things on the macroscopic scale. So now we can define our new tensor A1 as the following tensor product of all of these f's in the following expression. So note that for A0, we only needed 2 f's to describe it, and for A1, it comprises 4 total f tensors. So we have therefore halved the total number of tensors we need to describe our whole grid, so there are n over 4 A1s. The final step of the tensor renormalization group method is to normalize A1. So these tensors can start to have extremely large numbers contained in them if we don't normalize them after each step. So we define some number, let's call it W, where W is the Euclidean norm of the tensor A1, for example, and we factor this out of the tensor, and we get this A with the A1 with the tilde on the top, which is our new normalized tensor, and we continue on in the algorithm with A1 with the tilde on top of it. Doing this at every step and tracking the W's will be sufficient to construct the free energy and basically calculate all of the thermal equilibrium properties of the Ising chain. So what does this look like in practice? Well, we started with the partition function being exactly written in terms of a tensor trace, with A0 being our first tensor. There was n over 2 of these tensors, and when we applied our approximation scheme and got A1, remember that this was in fact an approximation. We ended up with n over 4 tensors. So then we normalized A1 and pulled out W1, which we get n over 4 terms out of that product. And from here we can straightforwardly see what the expression would be if we did capital S of these iterations of the algorithm. We would get this, much longer expression. But notice here that if we say that we perform the algorithm S total times, and then we stop the algorithm, the total system size that we would have evaluated is a system size of 2 to the power of S plus 1 total spins on our entire two-dimensional lattice. So now let's take a quick look at some results. We can write the free energy as we have done in past videos in terms of the partition function z, which is exactly what we're evaluating here. And here we can freely write the free energy per site, which we identify as the lowercase f in terms of our w's that we're producing from our algorithm. Again, note the approximation symbol signifying that this is not an exact calculation. So here we've divided out the total number of sites and took the logarithm of the partition function that we were evaluating, and we're going to ignore the final term of the tensor trace, as it shouldn't be important for the calculation. We will also numerically investigate the magnetization, which we define here as is the derivative of the free energy per site with respect to a changing magnetic field. The next thing to note is that the two-dimensional Ising model on a square lattice is actually exactly solvable. The solution was written by Lars Onsager in the 1940s. The solution is provided in the thermodynamic limit and when the field is set to 0. So we will definitely review this solution at a later time, but for now we will just state Onsager's solution to this model. So the expression for the free energy is the following large integral expression. The contents of it actually aren't that important, but just know that it exists and we just have to evaluate it numerically to compare to our algorithm to see how good our algorithm is. So K here in this expression is given by the following expression that's dependent on the inverse temperature, and this model also goes through a thermal phase transition, which is most importantly characterized by the spontaneous magnetization at finite temperature. So some critical temperature Tc exists such that once we pass it, we get the following magnetization curve. And remember, importantly, this is at 0 magnetic field. So H in our former energy expression is 0. Okay, so just a quick example of how this algorithm might look once you code it up and you try to reproduce some results. So here we're going to do the algorithm for chi prime is 21. S here will do 23 iterations of the algorithm, which means we have 2 to the 24 spins sitting on our lattice. And for the parameters that we showed at the beginning, this means that the critical temperature should be approximately at about 2.27. So the first thing we can show is the plot for the free energy. In blue we have our algorithm, and in red we have Onsager's exact solution. And we see that the algorithm, at least at the scale that we're looking at it here, appears to perfectly approximate the curve. The green vertical line here tells us where the critical point is, and that sort of tells us, that's the region of interest for the model that we sort of want to get at. If we, however, move on to magnetization, and we similarly have the same color scheme, we see that the algorithm actually sort of struggles a little bit around the critical point, but outside of the critical point region or the critical region, we appear to again match the curve exactly and reproduce the form of Onsager's exact solution to the model. Okay, so obviously the important question here now is, how would I actually code this up? So I did this in C++, and I used a library called itensor. Itensor is free. It makes your life a lot easier when working with tensors, and it's specifically designed for physics problems. In the description, I will leave a link to itensor's website, and specifically the link where they showcase example code for this exact problem. But that's it for today, everyone. I hope you liked the video and you learned something. If you did, feel free to like, subscribe, and leave a comment below.